Yes, it takes place in Berkeley, I believe. Where? Hotel Shattuck. That's right. And then we'll have a speaking event to be announced. We're working on it. Of course, the monthly pub crawl. Announcements, please silence all cell phones, devices that make noise. Restrooms are up this way and then down that way, down the hall. Emergency exits, there. If you have any food receipts, go ahead and put that into our donation. And we have t-shirts. If you want to buy a t-shirt for us, let us know. Okay, so to introduce Miriam, I'm going to go ahead and bring up Judy Bannister. She's going to introduce Miriam Diamond.
Good evening. We are pleased and honored to welcome Dr. Miriam Diamond. She works at SLAC, the Stanford Linear Accelerator. She is Canadian, born and raised in Ottawa, Canada. She got all of her degrees, including Ph.D. in physics at the University of Toronto, during which time she spent several months at the Large Hadron Collider in Europe, working because her specialty is experimental particle physics. So she's a very high-end physicist. And at SLAC, for a 2-year period, she is working to use quantum sensors to detect dark matter, hopefully. And then she is planning currently to return to her position as an assistant professor at the University of Toronto. So we are very pleased while Miriam Diamond is here in the Silicon Valley area to welcome her and take advantage of her expertise. Thank you so much for coming, and thank you, Miriam.
Thank you, everyone. How are y'all doing tonight? All right, welcome to the Quantum Game Show Uncertainty Principle. We are live in San Jose, and I'm your host, Dr. Miriam Diamond. The rules of the game are very simple. I put up a quantum product or service, and you tell me whether it's really quantum or whether it's just quackery. So, all audience members who stay until the end will win a prize for participating in this game show. So let's start with quantum curling shoes. The sport of curling became very popular here in America when you guys won the gold medal at the Olympics. So, are curling shoes actually taking advantage of quantum physics? No, that's right, it's just quackery. All right, next up we have the Royal Caribbean International Quantum of the Seas cruise ship. Anyone here want to go on a quantum cruise? No. All right, then we have Finnish Quantum Max dishwashing detergent. Is there any quantum physics going on in helping get your dishes clean? No. All right, the quantum garage door opener. Given the problems we seem to have with the doors here, maybe we could use a quantum door opener of some kind. It would be rather interesting to have a quantum door that was open and closed at the same time until you observe it. That would drive up your car insurance premiums. Next, we have the Quantum brand smartphone. Now, is this phone actually doing anything fancy, like quantum encryption or quantum computing? No, it's not. Then we have the Duracell quantum battery. Now, is this simply classical electrochemical reactions, or is there quantum physics special to this battery? No, there is nothing any more quantum about this battery brand than any other. Okay, next we have quantum dot televisions and solar cells. See these advertised a lot in Silicon Valley? Are they real? Yes, actually they are. Yes, this does actually take advantage of quantum effects. We have quantum random number generators. Have you ever seen these advertised? Yes, so they do actually use quantum physics to generate numbers that are not just pseudo-random, they are genuinely random, guaranteed by the laws of quantum physics to be random. Quantum encryption. You might have seen this advertised. Is it actually quantum? Actually, yes, it is. It uses the laws of quantum physics to guarantee the encryption cannot be broken by classical means. Then we have quantum teleporters. You heard of these? Yeah. So it turns out they are indeed quantum. However, they're not exactly really teleporters because we cannot use them to teleport any macroscopic objects as of yet. We can only teleport information and laser beams. Okay, then we have quantum computers advertised by places like Google and Microsoft in Silicon Valley.
Well,
are they actually quantum?
I wanted to get
Yes, they are.
Okay, that's yeah.
Some of you may have heard of quantum biology. Is this real or is it all hokum? So there are actually some real examples of quantum biology that I will be talking about. A lot of it is hokum. Only some of it is real. And by the end of this show, you will all be in a super position to tell the difference between the real and the hokum. All right, then we have quantum medicine and quantum healing. This one's a giveaway as soon as I put up Deepak Chopra. Yeah, this one's a giveaway for all you audience members. Yeah, this is hokum. Yeah, then we have quantum brains or quantum consciousness. There are all sorts of websites advocating this, most of them trying to sell you something. Is there anything to this? That's right, there's probably nothing to this. There have been some physicists who have seriously investigated whether any quantum processes or quantum computing might be going on in your brain. And I'll be talking about that later. We have no proof that anything quantum actually does happen in the brain. Then we have quantum jumping. So this proposes that you can actually jump to an alternate quantum universe using just the power of your thoughts. Has anyone here ever tried quantum jumping? No, so here in America, I'm looking for someone I can blame to jumping us all into an alternate universe of extremely low probability where Donald Trump is president. Yeah, and where I'm doing these kind of talks in Silicon Valley pubs in order to pay my rent. Yeah. So no one here I can blame? Okay, so in that case, you are all winners of the uncertainty principle round 1. We will be getting to round 2 a little bit later, and remember, stick around to the end of round 2, and you all win prizes. The prizes consist of a quantum, or a package, of dishwashing detergent. And if next time you want better prizes, ask your treasurer to pay me more. Yeah, don't forget to tip your speaker, folks. I hear all everything. All right, so as you probably realize, in order to get good at this game, it helps to know some of the basics of quantum physics. So what I'm going to be doing for the next little while is taking you through some of the main concepts that underlie quantum physics. Now, this has a reputation for being a very confusing subject. And that's because there is a lot of very difficult mathematics and physics involved in it. I will not be getting into any math here. This is a no math talk. It's going to be all just conceptual. And it's going to be from the point of view of what effects do these laws of quantum physics actually have. And a lot of people in popular culture tend to portray quantum physics as something that allows you to throw all the rules of physics out the window, and it's sort of anything is possible, anything can happen. And that's actually not at all the case. What happens is quantum physics has its own set of very well-defined laws that are different from the laws of physics that we're used to in day-to-day life, but they still are very well defined. And you cannot simply use quantum physics to justify any belief system you want, whether it's religious or spiritual or out there sci-fi stuff. There is a very well-defined set of laws you have to obey. These laws simply seem confusing to us because they're very different from the laws of classical physics. And so that's what I hope you all take away from this talk as sort of the number one most important message. All right, so let's start with what is quantum physics. The word quantum gets used and misused in a lot of different contexts, so it's important to sort of start at the very beginning with what is actually the definition of quantum physics. And it simply refers to our theory of the behavior of matter and energy at very small scales. And where it gets its name is from the very important underlying concept that various observables that in everyday life we are used to being able to take on any value are actually allowed at the very smallest scales, to only take on certain preset values. So that means it's quantized. And the most important of these observables is energy. So we are used to energy being able to take on any non-negative value, but actually in, for example, an electron or an atom, there are these energy levels. And in order to jump from a lower energy level to a higher energy level, the quantum system has to absorb a quantum of energy, where the amount of energy carried by this quantum is exactly this difference in energy levels. So in the case of an electron in an atom, it can absorb a quantum of light, which is known as a photon. You may know the photon as the carrier of the electromagnetic force. And actually the color of the photon is directly related to its wavelength and frequency, which is directly related to the amount of energy that it carries. So in order to excite an electron to a higher energy level, it has to absorb a photon of the appropriate color. And then to drop to a lower energy level, it emits a photon, which carries exactly the amount of energy to make up the difference. Another main concept that is very difficult to get used to in quantum physics is known as particle-wave duality. And this is the idea that every quantum system actually behaves both as a particle and as a wave, or it has some wave-like qualities and some particle-like qualities. And which one it appears to us to act like depends on what we're trying to measure about it, or how we go about measuring it. And so certain types of measurements, it will manifest to us as a particle, and in others it will manifest itself as a wave. And so every quantum system has what's called a wave function associated with it that is usually denoted by this Greek symbol phi. And so under certain observations or certain measurements, it manifests as having a certain wavelength, which is denoted by this Greek symbol lambda. And under other types of measurements, it behaves like a sort of jittery particle. And one of the very strange consequences of this is some properties of waves that we are very used to seeing in, for example, the ocean when we go surfing, actually show up in atoms and electrons and in places where we don't expect to see them. So waves have this property of interfering with each other. For example, if you have two waves that hit each other such that the peaks line up with each other and the troughs line up with each other, they basically add up to produce one bigger wave. And this is the effect that surfers love to take advantage of, for example. But if you have two waves knocking into each other and they're exactly out of alignment so that a peak matches up with a trough, then they actually cancel each other out. And so this effect is called interference, and when quantum systems crash into each other, their wave functions actually interfere. And so you get these very complicated patterns. And while you are not observing or not measuring a quantum system, it is in what's known as a superposition of states. And so it is actually in multiple states at once until you observe or measure it, and then the wave function collapses and it manifests as being only in one state. And so, for example, this is a three-dimensional representation of the position wave function of an electron. And where you see the peaks here, this is where you are most likely to observe it being. And these troughs are where you are least likely to observe it being when the wave function collapses. But while you're not observing it, it's actually in all these multiple places at once in a superposition. And this very strange property gives rise to what's known as the Heisenberg uncertainty principle, named after the physicist Heisenberg, who wrote it down in mathematical form. So technically, mathematically, it states that the uncertainty in a quantum system's momentum multiplied by the uncertainty in its position has to exceed or equal this fundamental constant known as Planck's constant, which is just some very small but not zero number. And so what it means is that you can never be exactly sure of where a particle is or how fast it's going, because neither of these can ever go to zero. And the more you know about where it is, the less you know about how fast it's going, and vice versa. So this leads to these kind of situations where, well, the quantum system is probably here, but it could be in various other places also. And it also leads to this bizarre effect which is known as quantum tunneling. In everyday life, if you have an object with a certain amount of energy and it knocks into a barrier, and the amount of energy required to penetrate that barrier is higher than the amount of energy that the object is carrying, well, the object can't get through the barrier. That's why things don't go through walls. But in the quantum world, you actually have an incoming wave function, and even if the average energy that's represented by this wave function is less than the energy of the barrier, there is still a non-zero wave function on the other end, with a reduced probability but not reduced energy. So it means that there is a small but non-zero chance that this object will actually show up on the other side of the barrier with exactly the same amount of energy that it had to start with, as if it somehow created an invisible tunnel through this barrier and just hopped through it. There, of course, is no actual invisible tunnel, so the word quantum tunneling is a bit of a misnomer. But this is a very well-defined quantum mechanical process. And then another very bizarre effect is known as quantum entanglement. And this happens where multiple quantum systems that appear to us to be distinct actually share a single underlying unfactorable wave function. And so that means that these two So that means that these two systems, which we observe as being different, are actually inextricably linked on a fundamental quantum level throughout space-time, no matter how far apart they are. If this sounds kind of romantic, if you're here with your entangled partner, give them a hug. I'm single, by the way. And so in a famous experiment here that some quantum physicists performed in a laboratory, they took particles on one side of a barrier and they arranged them in a cat. This is a reference to the infamous Schrodinger's cat, which was said to be in a superposition of dead and alive at the same time while it was sitting in its closed box until somebody observed it. And then the entangled partners of those particles on the other side form this sort of ghost cat image. This manifests a property known as non-locality, which means that something over here is somehow correlated with something over there. Now, this might seem like it would allow you to throw out all of the rules we are used to about information only propagating at the speed of light and things not being able to get from one place to another instantaneously. This is one of those cases where people use entanglement as an excuse to make, all sorts of sci-fi and religious and spiritual scenarios possible. It turns out that no, entanglement follows a very well-defined set of rules under which it cannot be used to send information faster than the speed of light. So it still obeys Einstein's principles of relativity. And this has been rigorously proven in setups in a laboratory where, for example, you have a source of entangled photons. Some of them go to one pair of detectors on one side of the laboratory and some of them go to the other. There are very well-defined correlations between the results here and the results there. There is never any information transfer. So using this property of entanglement does allow you to make all kinds of interesting quantum technologies like quantum computers and quantum teleporters, but it does not allow you to simply do anything you want. So these are some examples of quantum physics principles that often get used but also often get misused. And so I'm hoping that when you come across these terms, you will be able to recognize when they are being used properly and when they're being misused as quackery. All right, so now we will go to round 2 of uncertainty principle. We have 5 different categories tonight. And in each category, we are going to go through some details of quantum phenomena, what's real and what's quackery. So because we're in Silicon Valley, we are going to start with quantum computation. So this is a term that gets thrown around a lot, and you have to start by asking yourself, okay, what does a company really mean when I talk about quantum computation? The way that this whole quantum computation thing got started is basically Moore's law, which states that as time goes on, computers and computer components get exponentially smaller and smaller. And it was realized several years ago that eventually you would reach a point where that size is so small it's actually at the level of individual electrons or atoms. And these are quantum systems, which means that they behave according to the laws of quantum physics, which are not the same as the laws of classical physics. And so if you try and build a computer that works the same way your current desktop computer does, but just make it really small at the scale of atoms, it won't work because it's not quantum tolerant. So quantum effects are actually going to mess up the way your computer works. For example, if you have a wire, but it's on the quantum scale as a path from A to B, an electron can actually just tunnel out of that wire completely at random and show up somewhere else in your device and completely mess it up. So there's the idea that, we have to make sure these quantum devices don't sabotage us, but then actually physicists went a little bit further and realized we can use quantum effects to our advantage. So we can specifically build devices that harness quantum effects, and these can be exponentially more powerful than classical computing devices. One fairly straightforward way to take advantage of the laws of quantum physics is for storage, where you simply store the state of something in a quantum system, and instead of storing it as a bit, which is either a 0 or a 1, you have a qubit, and a qubit is in a superposition of 0 and 1 at the same time. And another way of putting this is that you can actually store a 0 and a 1 at the same time on a qubit. And then if you have 2 qubits and you entangle them or you link them together, then you can store 0, 0, 0, 1, 1, 0, and 1, 1 all at the same time. And then as you keep adding qubits, the number of things you can store at the same time goes exponentially with your number of qubits. And then not only can you use this for storage, you can use this for actual quantum processing, where you carry out calculations on qubits instead of bits, and you do exponentially many calculations at the same time. So this is the sort of quantum computer that companies like D-Wave and Microsoft and Google are trying to make. Now, some of them are not really full quantum computers. They are actually what's known as quantum simulators. And this is sort of like having a calculator rather than a computer. So there's certain types of operations that it can do, but not everything. And then there's a sort of idea of having a full quantum computer. And so you have to ask, is your quantum computer universal to all applications, or is it specific? And then you have to ask, does the quantum computer actually have what's known as quantum supremacy? So that means, is it more powerful than any classical computer ever built? And whether or not it achieves quantum supremacy depends on things like the number of qubits that you link together, something called decoherence time. What's meant by this is that systems that are in superposition are actually very fragile, because as soon as anything measures them or observes them, they fall out of superposition and collapse into a definite state. So if this happens in the middle of your calculation, the whole thing falls down like a quantum house of cards, and it crashes before your calculation is finished. So the quantum system has to be kept in superposition long enough for you to finish your calculation, and how long it's kept that way is known as its decoherence time. And then there's this whole issue of quantum error correction. The intrinsic randomness of quantum mechanics introduces all sorts of potential errors into quantum computing that simply have no equivalent in classical computing. And so you have to basically add more qubits to your system in order to correct for these errors. Otherwise, you will only get the right answer a certain percentage of the time. And it will be random whether you get the right or wrong answer. And you know, this isn't just random in the sense of, okay, it's random when my Windows crashes or when my PowerPoint crashes on the computer. No, it is actually random at a fundamental quantum level. And so if someone's trying to sell you a quantum computer, make sure you check out things like this. Something else that a lot of people try to propose is that quantum computation is somehow involved in either consciousness or in some sort of supreme being or deity or God. And so they would propose things like, oh, well, you know, you can have an all-powerful God who is omniscient because that God can do quantum computation. Or, you know, the reason that we don't understand human consciousness is that our brain is actually doing quantum computation, not classical computation in there. And that's why we can't build, you know, classical artificial intelligences that are as smart as humans are. And so in all that sort of thing, what you really have to remember is this issue of quantum superpositions being very fragile. So if you have an environment that is warm and wet and noisy, which is what happens in biology and in the real world, as opposed to these quantum computers built in labs that are usually operated at supercooled temperatures, so liquid helium or liquid nitrogen at least temperatures, and are completely isolated from everything around them in these, you know, specially built labs with thick walls and, you know, all sorts of seismic isolation in the floor and everything. You know, it's a very different situation. And then, you know, the number of qubits that you have to link together in order to do anything useful, especially when you take into account the need for error correction, you know, is actually pretty large. You have to have, you know, a couple of hundred qubits to be doing anything approaching significant. And so, you know, can you really have that going on in the real world or in a biological organism? So that's kind of what you have to ask yourself, and I'll be getting back to this quantum consciousness issue later. But I'm going to start with some more sort of basic quantum biology. So it turns out that there are certain processes that are very important to the workings of biological organisms, including ourselves, that do rely on the principles of quantum physics. So I'll go through some of the main ones here. The first and probably most famous is photosynthesis. This is basically nature's solar panels, where plants convert light energy in the form of incoming photons into chemical energy that they can use. And what actually happens is that the photon comes in, hits a special pigment, and that pigment has electrons in it with the energy levels such that the electron is excited by the incoming photon. And then the excited electron propagates to a chemical reaction center where that energy can then be forwarded to other chemical processes by the plant. And so the process by which the photon is absorbed in the pigment is fundamentally quantum, and even the process by which the excited electron makes its way over some path to the reaction center is a quantum process, and there might even be quantum tunneling involved in that process. The sort of companion process to this is cellular respiration, which is where cells take energy out of food and turn it into usable chemical energy. And what they're actually doing is they are taking a high energy electron and they're sending it through a whole set of chemical complexes, kind of like down a staircase, where at each step that electron is de-excited and gives off some of its energy in the form that's usable to the cell. And so all of these complexes are arranged in the cell membrane in this very complicated setup, and all of the movement of the electron through the membrane and the de-excitations of the electrons are governed by the rules of quantum physics. Going to a different kind of example, the human eye is actually a very sophisticated single photon detector. And we actually have trouble in the lab building photon detectors that are as sensitive as the eye. And the way this works is that at the back of your eye is an apparatus called which has these cells called rods and cones in them. And when photons strike electrons in these cells, they excite them, and then this actually turns into an electrical impulse, which propagates through the optic nerve from the back of the eye up to your brain, and then the brain interprets that signal as vision. So this is actually a very sophisticated photon detector that can not only tell whether there's light or not, but also tell what color it is based on exactly which of these cells was excited in what way. Another one of our senses, smell, actually also takes advantage of quantum physics, but to a bit of a lesser extent. The way that smell works is that a smelly molecule drifts up into your nose, and there are all sorts of different chemical receptors of different shapes in your nose, and the smelly molecule will bind to a receptor of the proper shape, kind of like two jigsaw pieces fitting together. And then when that binding happens, this sets off a little electrical signal which is sent up to your brain. But as you all know from when you're kids and you're doing jigsaw puzzles, sometimes two pieces that aren't quite the right shape do somehow manage to fit together. And so similarly, there are a lot of molecules out there that are actually different, but they're shaped similarly enough that they can bind to the same smell sensor. And so there's an extra level of discrimination where when a molecule is bound to the sensor actually detects the quantum vibrational modes of that molecule, and we can map the quantum vibration levels. They show up as these little peaks on graphs, and so that information is also sent to your brain, and that provides an extra level of smell discrimination, which you may regret the next time you run into a skunk, by the way. On my way here from Palo Alto, someone just outside SLAC had run over a skunk and the entire block stank, and I was cursing quantum physics. Birds actually have an extra sense, which we don't seem to have, which is that they can sense magnetic fields, and they use it like a little compass in order to navigate. So it's like they have a tiny compass embedded in their brain. And it took us a very long time to figure out how this worked. At first, people thought it was magic or sort of mystical, and they assigned some sort of mystical or possibly religious power to the birds. But no, it's It's actually just that birds have these special molecules in dedicated complexes at the back of their brain, where in their ground state, so this is in their natural undisturbed state, they have pairs of electrons at either side. But then when they are hit by a quantum of the electromagnetic field, one electron tends to jump onto the other side, and then you have a singlet state and a triplet state, and these two react differently to incoming magnetic fields. Not only the intensity of the magnetic field, but also the direction of the field matters. So when you're at a higher latitude, the field angle of the Earth's magnetic field approaches 90 degrees, whereas when you're at the equator, it's more parallel. And so birds can actually differentiate between these different field angles to figure out what latitude they're at and which direction they should fly in. And then something we have discovered very recently is quantum effects on DNA mutations. So as you probably all know, the DNA molecule is shaped like a double helix, where each rung of the ladder is made up of two of these very special molecules, adenosine, thymine, cytosine, and guanine. I think I pronounced those all correctly. If there's any biologists in the audience, please correct me. And so these are sort of the four letters that make up the DNA alphabet. And if one letter somehow gets misspelled as a different letter, this is known as a mutation. So there is a certain process which is known as a tautomeric shift that can happen when the DNA is unzipped and the cell is either reading it or replicating it, and the random quantum mechanical processes cause one of the electrons in the hydrogen bond between these two members of the rung to actually jump over into a different position where it's not supposed to be. And then these bases rearrange themselves in a way that they're not supposed to. You get an anomalous base pair form, and you get what's known as a point mutation. In other words, one letter misspelled. Now, in most places in the genetic code, this makes no difference, but there are certain places where, a one-letter misspelling can make a big difference, and you all know that from Donald Trump's tweets. In the vast majority of his tweets, changing one letter makes no difference because it makes no sense anyway, but for certain phrases that are actually cogent, changing one letter in his tweets may suddenly trigger a global thermonuclear war. So, don't tell anybody that I used quantum physics and Donald Trump in the same sentence. It's just, it's just crazy. Oh, by the way, also don't tell anyone from the Department of Energy, where I'm officially a contractor, that I'm making Donald Trump jokes, because then I will get deported back to Canada. Yeah, free trip home courtesy of ICE. Yeah. If, on the other hand, you want the DOE to give me more funding, email Rick Perry, my director's boss. Yeah. Anyway, enough of that. So speaking of Donald Trump, now for some quackery. Quantum medicine or healing. So this whole sort of subject claims that you can take advantage of quantum processes to somehow change the way that certain biological systems work in a way that benefits health. So, for example, the fact that quantum physics is sort of involved in cellular respiration, well, maybe we can use this to preserve or regenerate cells. Because quantum physics can be involved in gene mutation, maybe we can somehow harness quantum physics to change the way that genes are expressed. The idea behind homeopathy is basically administering very small amounts of substances that by the classical rules of physics, they should be small enough to make no difference whatsoever. Well, quantum physics is the realm of the very small, and so maybe some quantum physics effects allow very small doses of things to have a significant effect. If this sounds like a very ill-defined argument, that's because it is. It's complete nonsense. Then there's this whole idea of, well, if you can excite quantum systems at different energy levels by having them, absorb quanta of energy from things like fields or vibrations, maybe you can expose yourself to certain fields or vibrations and, jump the energy levels of your body or of your mind or something. No, it doesn't work that way. And then there's this whole general category of mind-body frontier things. The idea here being that you, as an observer, affect a quantum system simply by observing or measuring it because you can cause its wave function to collapse. And so if using your mind or your brain, you can sort of use your power of observation on your own body to collapse your body's wave function somehow differently, you can change the way that quantum processes are going on in your body. That's complete nonsense. What's a little bit less clearly nonsense is this whole sort of question of quantum brains or quantum consciousness. And this can sort of fall into two categories. One is a question of whether consciousness is somehow fundamental to quantum physics and therefore to the universe. And the other sort of category is whether quantum processes can go on in brains. So I'm going to start with this sort of idea of consciousness being somehow fundamental to quantum physics. Excuse me for just a second. There was a mathematical physicist by the name of Henry Stack who basically developed this theory where a wave function collapses due to its interaction with consciousness, and that conscious minds are somehow selecting one amongst all of the alternative quantum possibilities that can happen. And in this sort of a theory, if there is no consciousness in the universe, then there's nothing to collapse the wave function, and everything sort of remains in a state of superposition. This can be very easily sort of carried into the religious realm, where there's some deity or supernatural being who is observing the entire universe, and the consciousness of that being is what is collapsing all of the universal wave functions, and therefore somehow making our reality. So those arguments, the problem with them from a physics point of view is that we have no proof whatsoever that wave function collapse involves or requires consciousness. And you can have wave functions collapsing from one quantum system interacting with another quantum system, where one of those quantum systems is acting as the observer or as the thing during the measurement, where that quantum system does not have to be conscious. Okay, it can just be a particle of dust that drifts into our quantum computer and causes the whole calculation to collapse. And so unless we try to assign a consciousness to even that particle of dust, right, this whole argument sort of falls apart. But then you get into sort of more radical ideas. For example, Freeman Dyson. I actually got the opportunity to meet him a few years ago. He's a very, very fascinating scientist. We have some intellectual disagreements, but he's actually a very brilliant scientist. And he proposes basically the subatomic particles have to some extent minds of their own. And what he actually said was, mind, as manifested by the capacity to make choices, is to some extent inherent even in every electron. And so then the idea here is that everything, every quantum system in the universe has consciousness of some sort. Then there's Roger Penrose. I got a chance to meet him also. Once again, we have some disagreements, but he's a brilliant scientist. And he has this whole proposal of what he calls objective reduction, which is sort of an alternative to wave function collapse. And so basically what he proposes is that at the very, very smallest scale, so it's what's known as the Planck scale, which is the smallest that can possibly be observed. Space-time, he thinks, is not actually continuous, but it's actually quantized. And so just like things like energy are quantized, so is distance and time at that scale. And so then you have all kinds of quantum gravity effects. Curved space-time is actually related to gravity, as Einstein showed us in relativity. And then he proposes that basically in the midst of this quantum gravity, there is some sort of a non-classically computable influence, which causes the wave functions to collapse. It looks to us like it's random, but it's not actually random. It is governed by this sort of quantum gravity non-computational influence. And furthermore, he proposes that quantum computers and also consciousness tap into this non-classically computable influence. So this sometimes gets carried into the philosophical realm, where going all the way back to the ancient Greeks, there was sort of this idea of a physical world and a mental world and a Platonic realm. And this Platonic realm has been associated now with Penrose's idea of non-classically computable fundamental influence, literally woven into the fabric of space-time. And so, there you have a wave function collapse and consciousness both coming from the same mechanism, which, unfortunately, not only can we not observe it being all the way down at the Planck scale, but we have absolutely no proof that it even exists. This is only a hypothesis. It's what's known as an interpretation of quantum mechanics. There's actually no way to tell the difference, at least not yet, between what it predicts and what more usual interpretations of quantum mechanics predict. And so then there's this whole idea of whether quantum processes can happen in brains. So, for example, Roger Penrose teamed up at one point with actually an anesthesiologist named Stuart Hameroff to basically try and figure out what part of our brains are doing quantum computation with this sort of non-classically computable influence. And they proposed that qubits are formed collectively on structures known as microtubules in neuron cells in the brain, and furthermore that they can be entangled with each other through basically the gap junctions of neurons over which, for example, quantum tunneling can happen. There was then another group of theorists led by Umezawa who developed what he calls a quantum field theory of brain dynamics. So quantum field theory is what we normally use to describe systems of subatomic particles, and the way that they interact is one of the things that I specialize in. And so he applied the principles of quantum field theory to a brain system where you have sort of long-range quantum coherence between different parts of the brain. And this turns out to be especially useful in modeling memory storage and retrieval, which this other scientist, Cielo, picked up on. And so the idea there is it sort of explains the large memory capacity of, for example, the human brain by saying, well, if there's some quantum storage going on, then when you add a new memory, you don't necessarily have to erase an old memory because you can store the new one and the old one at the same time in sort of this state of superposition. And then there was another group of neurosurgeons led by Carl Riebham who came up with what he calls holonomic brain theory. So the word holonomic comes from the root holon, which is a quantum of information in what's known as quantum holography. And so here, not only are things like energy quantized, but also information itself is quantized. And then quantum processing occurs on quanta of information, and these quanta are processed, he thought, by dendrites in the brain. So here's the catch with virtually all of these schemes.